Hello everyone. Topic for this poster presentation is towards intelligent reconfigurable wireless physical layer. This work has done under the supervision of the Dr. Sumit Darak. Next generation wireless network are expecting to be enable smarter agriculture, remote healthcare access, industry 4, and intelligent transportation. Next generation wireless networks are expecting for multitude of the services and devices. This type of services cannot be fulfilled with the existing physical layer, as the existing physical layer is not flexible. It lacks flexibility, and it depends on the upper layer for the various decision making tasks. It lacks in the learning the environment. So to overcome all these problems, we are proposing intelligent and reconfigurable physical layer to fulfill all these requirements. Reconfigurable file can adapt to the changing unknown environment, but it needs intelligence to learn the environment so that it can dynamically choose the reconfiguration parameter. We design and realize the end-to-end physical layer, which is intelligent and reconfigurable on Jinx system on chip, which is consisting of the ARM processor and a field programmable gate array as a programmable logic. We integrate MAB architecture with the wireless physical layer and demonstrate the functionality of the intelligent and reconfigurable on wireless application. We demonstrate the intelligent on the PHY selection of the modulation scheme and the wireless channel to improve the throughput. So this is the proposed intelligent and reconfigurable wireless PHY. It consists of the transmitter and the receiver and the MAB algorithm. Transmitter wireless PHY and the receiver wireless PHY and the MAB architecture is implemented in the PL portion of the Jinx SoC. Whereas the transport block and performance analysis is on the PS system of the block. Transport block provide the data to the transmitter PHY. Whenever it receive the control signal from the upper layer, it transmit the data to the transmitter. In our case, we are assuming that it already stored the data into the memory, so it transmit the data to the transmitter whenever it get the control signal from the upper layer. Data channel coding blocks generate the bits according to the modulation scheme, and the data modulation block generate the complex in-phase and quadrature component in signed 16-bit in Q115 format. And this design is according to the 802.11 standard. So it consists of the 64 data subcarrier, and out of this 48 data carrier, 4 pilot symbol and 12 null subcarrier. Pilot are basically BPSK modulated, and it is pre-generated according to the index of the data carrier. So it is already stored in the memory of the system. And resource mapping block basically map the data modulation and pilot according to the index, and it is basically serial to parallel converter, and this is followed by the IFFT. We have used the inbuilt chaining IP block for implementation of the IFFT, and output of the IFFT is a serial timing signals, and after that it is followed by the preamble addition. We have used preamble symbols for the synchronization, as the transmitter and receiver are not synchronized, and after the preamble addition we send this data on one of the channel of the different fading coefficient channels, and at the receiver we detect the boundary according to the preamble symbols and detect the frame, and passed to the data to the basically waveform demodulation, and after that channel equalization and data demodulation. So in basically this MAP algorithm provide the information to the device configuration block, and it can basically MAP block relies the learning algorithm that provide the input to the device configuration block. We can say that transmitter PHY, MAP, and the device configuration block decide the which channel to be selected in subsequent time slot, and that is based on the learned distribution of the selection channel. And according to that, one of the modulation scheme is selected. So we can say input transmitter PHY is input to the transmitter PHY is the modulation scheme channel and the transport block of the appropriate size. So this is the proposed intelligent and reconfigurable PHY architecture mapped on the Zinc SoC. We have mapped via the hardware software co-design. So it consists of the basically one wireless transmitter PHY having two modulation capabilities, QPSK and 16 QM, one wireless receiver PHY having two demodulation capabilities, QPSK and 16 QM, and one reconfigurable comparator where it compare the inputs and do the performance analysis and calculate the bit error rate. And this system consists of the online machine learning algorithm with having three unique function calculations. So for online machine learning algorithm, we have used multi-arm bandit algorithm for decision making. So because we know that the decision making in uncertain environment is a challenge, and bandit provide a simple solution for such kind of dilemma. Decision making map can identify the best arm among the several unknown several arms in an unknown environment. Here arms we consider as a channel, so we use map to select the best channel to transmit and it sends according to the channel statics. They guarantee the optimal balance between the exploration and exploitation. Exploration means select all the arms for a sufficient number of times, and exploitation means select the best arm as many as times as possible. So map algorithm consists of initialization and parameter update block and QF calculation block. So this is the formula for QF calculation block, and depend on the this is UCB QF calculation block. We have used its variants also, UCB-T tunable and UCB variance QF calculation also. And this is the channel selection block. So we analyze and do the performance and complexity analysis. We select the channel K and N is 10,000. We run the experiment for 10,000 cycles, and we have 6 different channel statics for performance evaluation in a different environment. We consider the channel as mentioned as showing in this presentation. So we compare the total number of bits received in error in percentage for 3 different channel selection. We consider one is the oracle channel, and one is the random, where it can in random selection scheme it can select any random channel. Oracle is the best channel. Which channel is the best? It select the best channel only. In the proposed is the where it select on the basis of the learning from the map algorithm. So it can be clearly seen from the results that proposed is performing much far better than the random channel selection scheme, and it is near to the oracle scheme. We repeat this experiment for the 3 different modulation selection approach. One is the fixed 16 QM selection. Every time we select the modulation scheme only QM 16, then fixed QPSK, and then proposed solution that is based on channel based modulation switching scheme, map based approach. And we can clearly see from this results that proposed one is much better than the 16 QM, and it is in terms of the bit error rate, it is approaching to the QPSK modulation scheme. So in this way we can get the you can say the benefit of the higher throughput of the 16 QM and lower bit error rate of the QPSK if we select on the basis of the map. So we do the we compare the total throughput in megabits per second and the total number of transmission required to meet the bit error rate of 1%. We take the penalty 30% penalty in time for whenever there is a required for the retransmission. So the data which is mentioned in the bracket in this table, which is retransmission. So we are able to see that the proposed is performing better as compared to QPSK and QM in terms of the throughputs. So when channel is best, it's every time it's selecting the best channel, and its throughput is quite high, and retransmission is number of retransmission is less as compared to the QM 16. So we also analyze the in term of the resource utilization from the Velcro approach, and it is clearly see its reduction in the LED uses, flip-flop and DSP as compared to the Velcro approach. So we also compare the results in terms of the latency for different channels. For example, we consider if channel 2, 3, 4, 5. So we compare the latency for different architecture, for example, single point floating point, and then we compare the results for different word length as well as in terms of the latency as well as the resource utilization. And when word length is decreased, we find out that there is a reduction in the resource utilization, and it is performing better as compared to the Velcro approach. So we present this novel design and implementation of the intelligent and reconfigurable physical layer for the next generation wireless transceiver. And we integrate this architecture with the MAB algorithm, and that offer intelligence to the dynamic partial reconfiguration based reconfigurable file. Proposed architecture offer 3 megabits per second higher average throughput as compared to the others one, and the lower resource utilization as compared to the Velcro approach. It is also showing lower power consumption compared to the conventional file. Thanks. Thank you so much.